All right, classwork 7.3. We are trying to understand what the graphs of the other four trig functions look like. So we know what the graph of sine x and cosine look like. What are the other graphs? Starting with secant. Secant is the reciprocal of cosine. That means every single y value that we're used to seeing on cosine, the reciprocal of that y value is on the graph of secant. That's why I asked here in part B, what is the reciprocal of 1? It is 1. What is the reciprocal of -1? It is -1. So you want to know that at those points where cosine is equal to 1 and -1, those are the only points that cosine shares with the graph of secant x. The thing that I'm trying to explain with part C is that when cosine is equal to 0, secant is having a vertical asymptote because that's what happens when you reciprocate 0. So that's where I want you to see that cosine is 0 at pi over 2, negative pi over 2, 3 pi over 2, all these numbers that I'm circling. So everywhere that cosine intersects the x-axis, that is where the asymptotes are for the graph of secant. Whoops. And trying to line things up. Okay. Now, the next thing that I'm talking about is numbers that are between 0 and 1, as well as numbers that are between 0 and -1. And what are those reciprocals? And just realized I need to put in here vertical asymptote. So the size of the reciprocals of numbers between 0 and 1 are numbers that are greater than 1. The reciprocals of numbers between -1 and 0 are negative numbers less than -1. And I'm trying to point out in that the understanding that when I reciprocate, say, 0.9, it's bigger than 1. When I reciprocate 0.5, if I look at where 0.5 is, about this value here, the reciprocal of 1/2 is 2. So it's only made it to about there. But if I start looking at the numbers where the y values are near 0 on the cosine graph, that's where it's suddenly asymptoting. And this creates a graph that looks like this. Then when I look at the section where the graph of cosine is underneath the x-axis, it does the same thing, but in the negative arena. And then I've got a nice graph of boom. This is just step-by-step me talking through on the document what I'm saying to you out loud. So here it is. What you see here, these are the graph of secant. And I've got asymptotes drawn in there. Asymptotes aren't the graph itself, but they are what the graph is heading to. And let's see, was there something else that I had on there? By the way, I fixed the answer key to the classwork last period. So that's fixed. All right. Then cosecant is very similar to the way the graph secant looks. Cosecant is the reciprocal of which trig function? Let me see it in chat. What is the reciprocal function of cosecant? Sine. Good. So basically what you can do is when you know you need to graph cosecant, you can do a little dash graph of sine. And I'm trying to find where I'm at over here. Give me a second. Here we go. You can see in blue, this is the graph of sine. And I can take all the y values of sine that are equal to +1 and -1 and know that those are shared points between the graph of sine and its reciprocal cosecant. And when I am dealing with numbers that are positive between 0 and 1, that will cause the graph to become asymptoting in that manner. And so you can see the graphs. Whoa. Okay, I don't know why it keeps doing that to me. But anyway, these are the graphs right here that create cosecant. Now, the range, the y values that these graphs go through are basically all real numbers, except they do not exist between -1 and +1. So the range of secant and cosecant are from -infinity to -1, including -1 as I go from way underneath the x-axis as I head up. And then nothing exists between -1 and 1, and the graph comes back into existence at y = 1 up to infinity. Now, the domain of secant, if you look back at secant, secant is the reciprocal of cosine, and right now I'm having trouble finding where I'm at. Okay, yeah, this is secant, reciprocal of cosine. The places where cosine is equal to 0, that's pi/2, -pi/2, 3pi/2, and there's a nice pattern to that. If I basically just write pi/2 plus any pi times n, that those are the individual numbers that are not in the domain. Other than that, the domain of secant is all real numbers. So for secant, it's all real numbers except for starting at pi/2, any addition or subtraction of pi for any number of times, where n represents all integers, positive and negative. Cosecant's domain is everything except where sine is equal to 0. And actually, I could have said just pi times n with that. But I was trying to emphasize that you can look at one of the numbers where you know cosecant has a vertical asymptote and add pi n to that, just to make it a little bit more clear. Both of these functions have periods that are 2 pi. So every 2 pi radians, the cycle repeats itself and does the same thing again. And that's what you need to know to get started with the graphs of secant and cosecant. Now we're turning to tangent first. Now, this is a little bit tedious. I realize that. But I want to do what I can to help you understand the graph of tangent and the graph of cotangent. If I bring up the unit circle, I can show you these a little bit faster with that. So let me find my unit circle if I can remember where I located it. I can find it. If I go here, give me just 1 second. Okay, so one thing I've been trying to emphasize is the issue of tangent is slope. So when I'm dealing with angle 0 degrees and 180, the slope is 0. That means the value of tangent is 0 when x is equal to 0 and when x is equal to pi. Going back to the unit circle, the slope of the line that goes through pi over 6 is 1 divided by root 3. I can also look at it as my sine divided my cosine. And the same goes for opposite that at 7 pi over 6. So positive 1 over root 3 for pi over 6 and for 7 pi over 6. And I can keep going back and forth. I don't know if your attention is going to actually stay or not, but at pi over 4, you have a slope of 1. At pi over 3, you have a slope of root 3. And they're opposite the other side of the circle, so plus pi, they have the same thing. So I have a slope of 1 at pi over 4, and pi over 4 plus pi, I also have a slope of 1. I have a slope of root 3 at pi over 3, and opposite plus pi from that also at 4 pi over 3. But when I go to pi over 2 and I look at the unit circle, if I can find it, there we go. If I look at the unit circle, I can see that when I'm located at pi over 2 and 3 pi over 2, if I draw a vertical line, that has an undefined slope, which is in a way an infinity slope, but it's undefined at those places, at pi over 2 and at 3 pi over 2. Now, I decided to make this chart only go from 0 to 3 pi over 2 because I needed to begin to show you the repetition, but I didn't want to do overkill, which this probably borderlines on overkill, I know. So over here, I'm focused on where I have negative slopes. Looking at the unit circle again, my negative slopes are at 2 pi over 3, negative root 3. At 3 pi over 4, negative 1. At 5 pi over 6, negative 1 over root 3. And again, they share their slopes with the angles that are pi away from them. And so that gives us these numbers. When it comes to cotangent, cotangent is the reciprocal of every single one of these. So the reciprocal of 0 is infinity. Undefined, I have a vertical asymptote there. The reciprocal of 1 divided by root 3 is root 3. 1's reciprocal is itself. Reciprocal of root 3. And reciprocal of the undefined takes us back to the 0. And then the negative numbers as well. So what I want you to do is plot those numbers. There we go. Plot those numbers. It doesn't have to be plotted perfectly. But I want to point out to you that the square root of 3 is approximately 1.7, and 1 divided by root 3 is approximately 0.57. So everyone look at plotting these points. And I'm going to go back over here and I'm going to plot the point 0, 0. Then if I look at, what number am I thinking of? Pi over 6, about here-ish. That was like 0.5 something. So maybe a point about there. When it comes to pi over 4, I got a value of 1. When I got to pi over 3, about here, I had a value that was 1.7-ish. So maybe about there. But with tangent being equal to sine divided by cosine, when cosine is getting to be near 0, sine is near positive 1 or negative 1. And this fraction, when cosine is near 0, is heading toward infinity. Cosine is equal to 0 at pi over 2. That gives me vertical asymptote there. And if I try to follow along with what these points are doing, it's basically just kind of heading up the asymptote. And then I can continue and plot more points, and what I'll end up getting is that let me try and plot a couple of those. So there's a couple of the points that we found, and then that is not what I intended to do. And then the graph goes down. Now what I'm going to do is I'm going to circle the numbers where cosine x is equal to 0. So that's negative pi over 2, 3 pi over 2, and so on. And I'm going to draw asymptotes at each of those. And the tangent graph in between asymptotes just goes wiggly up. Wiggly up is what it does. And I know that people look at it as being similar to the graph of x cubed, but realize that x cubed is flat in its center. Tangent is not flat in its center. And x cubed also doesn't follow asymptotes, and it's just one single graph. But if it helps you to remember about what it looks like, you can think of it as being similar to looking like x cubed. When I go and I plot the points on cotangent, I end up realizing that cotangent is cosine over sine. everywhere that cosine is equal to 0, cotangent is equal to 0. So I'm going to plot those points. Cosine is 0 at pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. And everywhere that sine is equal to 0, cosine is equal to either 1 or negative 1, and I'm getting an infinity number situation. And that's going to create vertical asymptotes at the places where sine is equal to 0, which is 0, pi, 2 pi, 3 pi, 4 pi, and pi. Now, if I start plotting some of the points of the cotangent graph that we found a moment ago, or take a look at the fact that at pi over 4, cotangent is equal to 1. And take a look at the fact that at 3 pi over 4, cotangent is equal to negative 1. And then if you plot a few more points, or maybe you don't need to plot a few more points, you will see that cotangent actually looks like a backward tangent graph. Tangent, if you go left to right, heads upward. But cotangent, if you go left to right, heads downward. And it just continues to repeat its cycle over and over again. So here are your graphs of tangent and cotangent. And I want to make sure that you are clear on number 6 and 7 because it can help you tremendously if you take a math class again where you need to use trig. This will help you to remember how to come up with these graphs. So what I'm trying to say over here on the right is tangent x is equal to sine divided by cosine. This was meant to be a division bar. That's what I was hoping you would see. I don't know if you saw it that way. And with undefined, I don't know if I answered your question on that, but it plots as a vertical asymptote when it's undefined because it's basically heading to infinity, or it is heading to infinity. So what you want to realize is that here we go. When sine x is equal to 0, when it comes to tangent, sine is the numerator. And that means that tangent has an x-intercept when sine is 0. But when it comes to cotangent, sine is its denominator. And if its denominator is 0, I have a vertical asymptote. And then when cosine is equal to 0, they reverse the process. Cosine is the denominator for tangent, and it has a vertical asymptote everywhere cosine is equal to 0. And cosine is the numerator on cotangent. So that means when cosine is 0, you have x-intercepts. Know that what I'm trying to do is explain to you the graphs. Ultimately, you are allowed to just kind of memorize them. And we'll get to that. But I think it's very important to take a look at where things are coming from and how they are connected. If it doesn't make sense how they are connected, you can still memorize the graphs. The range means what are the y values. And with tangent and cotangent, they have a range of all real numbers because that's looking at vertically, they exist completely up and down. Their domains are all real numbers except for where the vertical asymptotes are. Tangent has vertical asymptotes at pi over 2 and every addition or subtraction of pi any integer number of times. Now, I could have said just pi n for cotangent, but I wanted to emphasize a starting point. Basically, for every multiple of pi, that is where cotangent is missing or is lacking domain. Now, the thing that's interesting is tangent and cotangent start repeating their cycles every pi amount. So sine, cosine, secant, and cosecant, the periods of all four of them are 2 pi. But tangent and cotangent, the periods are pi. Now, what do you need to be able to do? You need to be able to, with the tests that is going to come up, you're going to be able to have notes. That means you're going to be able to have the graphs of all these functions right there next to you. So what you can do is use these to help you in graphing the example problems. Example problem number 1. Let me get over there. All right. This is asking you to sketch 2 cycles of each of the following graphs. Now what I'm going to do is I'm going to first draw the parent graph of secant x. And I'm going to draw it in blue. And what I'm going to do to help me graph this, if I didn't have notes next to me, I remember that it is the reciprocal of cosine. So if I draw a cosine graph, and yes, you could do that. In fact, that's the way I used to do it when I was in school, and it's perfectly fine to do that. And the question was, could you start drawing cosine of 2x? And then, in fact, I'll show you guys that way after I do this. So here's the graph of cosine, 1 cycle, and I need 2 cycles, so I'm going to draw another one. Now, the great thing is that you can look at that graph of cosine, and everywhere that it crosses the x-axis, draw an asymptote. And everywhere that it has a relative maximum, relative minimum, those are points that are shared with its reciprocal graph. And then from there, you want to do your best to remember that the graph basically ends up looking like this. And I'm going to erase my cosine graph just so you can see a little bit more clearly. That this would be 2 cycles of secant x. I want to draw secant of 2x. So when my x is multiplied by 2 in the equation, the graph is going to take the current x values and divide them by 2, and you get squished toward the y-axis. That means that My vertical asymptote here at pi over 2, I'm going to divide pi over 2 by 2. That'll give me pi over 4. And that is where that asymptote has been squished. And for the sake of me not drawing over itself, I'm going to show you that this is what, so here's the graph of secant, and then dividing those x values by 2 would look like this. So it just squishes it. And that's 2 cycles worth. Now, what Jason was saying is actually, you may like going about it that way. And it does work, and I'll show you that it works real quick. I could go straight to the graph of cosine 2x because this is equal to the reciprocal of cosine with the same angle. When I graph the cosine of 2x, the period of cosine has been divided by 2. When x is equal to 0, no change. But normally I have 0 at pi over 2, cut it in half. Normally I'm at -1 when I reach pi, cut it in half. Normally I'm back to 0 at 3 pi over 2, cut that in half, and that's going to be 3 pi over 4. And normally at 2 pi, my cosine is back to 1, cut that in half, and that's pi. So if I graph cosine 2x, and let's go ahead and draw 2 cycles of that. I can actually graph my secant graph off of that. Everywhere that it has an x-intercept, I have a vertical asymptote. And additionally, everywhere that it is equal to its highest and lowest points, their secant also graphs. And there you go. Now let's move over to cotangent. When you look at what this is saying that we're going to take the parent graph of cotangent and we are going to move it which direction? Let me see in chat. Which direction am I moving the parent's cotangent graph? I'm going to move it left pi over 4. So I can kind of map this out. Cotangent normally has asymptotes. And let me write in, cotangent is cosine over sine. Cotangent normally has asymptotes at the place where sine is equal to 0. So my asymptotes normally are 0, pi over 2, and all the pi over 2's. Or no, I'm sorry, I just messed up. I was mixing things up. Start again. Sine is equal to 0 at 0, pi, 2 pi, 3 pi, 4 pi, negative pi. These are where the asymptotes are for a regular cotangent graph. Cosine is equal to 0, where cotangent is also equal to 0. So normally, cotangent goes through the point at pi over 2, and 3 pi over 2, and negative pi over 2, and so on. but I only need to graph 2 cycles of this. I'm going to just plain shift everybody left pi over 4. So if I take where I was going to have an asymptote at 0 and shift it left pi over 4, then I draw it here. If I was supposed to go through the x-axis at pi over 2, I shift it left pi over 4, and I have a point. Then I was going to have an asymptote at pi, shift it over pi over 4, left 1 unit. And then I'm just going to stop right there. And then this point moved over. I'm going to erase the points that I had to move so that they don't get confused. And now, if you remember that the graph of cotangent only heads downward, then you can pretty much start drawing it. It also helps if you remember that in between the asymptote and the x-intercept is where you have the values of 1 and -1. And then I'll show you a picture where it is graphed by a graphing calculator, or Desmos actually. All right, now in your homework, you're going to graph these, and what did I do? Oh, I have a variety of pictures in the answer key just to help you out, showing you these are the final answers here, but these were the original graphs. And this is looking at the original and the answers together so you can see what happened. All right, now we are on to our last couple of problems. We're going to write an equation. All right. Yeah. No, we don't have a quiz today. I'm not doing a quiz. Right now I'm honestly thinking it's best if I just kind of forego tests and quizzes for the next week, because I know that stress levels are high right now and you're trying to remember all this trig from having been off of it for 2 weeks. I can stay after class and you can talk, yeah. Okay. So this problem is asking you to write an equation, but the only change is just whatever x is multiplied by. There are different ways that you can do this. One way that you can do this is when you multiply x by a number, it will not change what happens when x is equal to 0. But it will either stretch the graph away from the y-axis or compress it in, like the, never mind, I can't think of words, or compress it in toward the y-axis. Normally, where does tangent have its asymptotes? And that's where you can go and you can look at the graph. When you're taking a test, you'll have the notes. You can look at the graph. You can see that tangent normally has asymptotes at pi over 2, negative pi over 2. But right now my asymptotes are here at 3 pi over 2 and negative 3 pi over 2. So one way you can think of it is, what do I have to do to pi over 2? What do I multiply it by to go from pi over 2 to 3 pi over 2? So I am taking my parent graph and I'm looking at where things are normally located on my parent graph. I have to multiply by 3 to get to where the new graph has those same things. Correct. So what I have to do to the graph horizontally, I have to do the opposite operation to the equation. That means if I see that the graph is being horizontally stretched out to be wider, then I have to actually divide x in the equation. But if I'm squishing the graph toward the y-axis, then whatever I'm dividing those x values by on the graph to squish them, that's what I need to multiply the x by in the equation.
Wait, Miss Blanchard.
Yeah.
I thought for the tan, or for the regular tan graph, at pi over 2, I thought that would be 1. Isn't it?
You know, I may have confused you by changing the layout of the tick marks. Because in the previous graphs, I have tick marks at every pi over 4. This one I have tick marks at every pi over 2. And I should probably change that because I'm realizing that that might be a problem. Yeah, I understand. And I need to change that so that these graphs also do the pi over 4 tick marks. But that's one way to look at it. Another way to look at it, I have in the answers. I'm showing that one cycle is created from negative 3 pi over 2 to positive 3 pi over 2. That makes the period of this tangent graph to be 3 pi. The period of a normal tangent graph is pi. So I can see that if I have to multiply the normal tangent graph's period by 3, then I need to divide the equation's x by 3. And so we're getting that this is the answer. Then I'm going to head back over here and look at our last problem. Woo, last problem! And I will allow you to leave once we are done with this last problem. So hold on, here we go. Cosecant. If you look at what this is showing, this is a multiplication and outside the function, and this is an addition outside of the function. Those are both vertical issues. If you look at a regular cosecant graph, the midline center horizontal axis is the x-axis normally. If you look at the little relative maximum minimum points, look at the y values of 5 and 1. The midline between those is halfway between them, and that means 3. The midline always is going to show the vertical translation. If I need to move the graph up 3 units, then I have to add 3 to the function. And remember that operations outside the function, you do the same operation as the graph shows you. But inside a parentheses with the x, the equation has to do the opposite operation that the graph shows horizontally. So I can see that my d is equal to 3. And what you can do from there is realize that the amplitude that we would normally get from the sine graph that this is representing, the amplitude from the center axis is 2 units. Right. But there's another issue. Normally, cosecant begins upward and then flips downward. So that means that A is -2. Now, I want to remind you, you're going to have the graphs in front of you, and you will have spent more time looking at them by the time a test comes around. And when you are looking at the cosecant graph that you have next to this graph, those are the things that you want to notice. I could also say this. If you know that cosecant is the reciprocal of sine, then realize that these are points shared with sine, and you can attempt to draw a sine curve in between them. And the vertical shift and amplitude of your sine graph is going to be identical to its reciprocals. And if you can draw a sine graph in there, you can see that it has a midline at 3, so up 3, and an amplitude of 2, but upside down. And you can see it's upside down because if you start at x equals 0, sine normally begins on the up, not on the down. Yeah, it is. That's helpful if you can draw that with the secant and cosecant graphs. And basically, whatever graph you come up with for the sine or the cosine that this is in between, those changes in the sine and cosine are identical to the changes to the equation of cosecant and secant, which is convenient. So that is the end of today's classwork. You have the whole weekend to get through, finish that, and then do these homework problems, but I recommend do them sooner rather than later, because right now you're remembering how to do them, and by Sunday night you will not remember, or at least you won't remember as easily. So have a good weekend. If you want to talk to me, stay, and I'm going to